Welcome to Pomodoro Joe for Tuesday, April 25th, 2023. Today we're doing LeetCode problem 2336, smallest number in infinite set. This is a medium problem. So you have a set which contains all positive integers, 1, 2, 3, 4, 5, etc. Implement the smallest infinite set class. So this has three functions: smallest infinite set, initializes the smallest infinite set object to contain all positive integers. Int pop smallest removes and returns the smallest integer contained in the infinite set. And finally, void add back, int num. All right, so add back adds a positive integer num back into the infinite set if it is not already in the infinite set. All right, and then we have an example. Okay. So I think this is going to be a fun one. So we'll put 25 minutes on the Pomodoro timer and we will get started. Okay, so for this one, we have an infinite set. So this set contains all the positive integers and it's infinite, which means we know right off the bat we cannot actually have a set that physically stores all of those values. So rather than having an explicit set of values, like stating these are the values in the set, we have an implicit set of values, meaning we just assume all these values are in the set unless we're told otherwise. So that's going to be our approach here. We're just going to assume that we have all the positive integers in our set, but then we have to track which ones we don't have in our set. So we'll have to keep some way of tracking that, either another set tracking all the values that are not in our set anymore, or some other way of tracking this. I think I already have an idea of how I want to do that, so we'll get into it. So one thing we could do, as mentioned, we could just keep a set of all the values that are no longer in our infinite set. So here we'll have some set. So let's see. We'll say self dot, what do I call it? Removed values, or removed nums. And that's just going to be a set. So we're going to keep a set of all our removed numbers. Okay, there we go. Then when we pop the smallest, we'll just have to go through our set, find the largest value there, and then basically do one more than that largest value, which will be our smallest value remaining. That seems confusing. Maybe there's a better way to do this. And if we were to do the add back, we would basically say, find the value in the removed nums and remove it from the removed nums, which is also kind of confusing. So I think I have a better solution here. So we know that this contains every single positive integer from 1 to infinity. So we know that when we pop smallest at the very beginning, we're going to be popping the value 1. Then if we call pop smallest again, we'll be popping the value 2. So we can actually just keep track of what is the smallest value we haven't popped yet. So we can just keep some integer that basically represents that smallest value we haven't popped yet. So let's do that. So I'm just going to call it smallest, and we'll set it to 1 because that is the smallest value we could possibly have. And then this removed numbers, instead of saying we're removing numbers, because when we pop 1, we don't actually want to say let's remove 1. We already know we've removed 1 because we're going to increment this to be 2. So this one will basically say anything up to this number has been removed because we've popped from 1, 2, 3, 4, 5. We've removed all those numbers. So we can basically say that anything in our set here is from this number to infinity. Then when we put numbers back, we basically just need to put them back into whatever we're missing, which is from 1 to our smallest number. So instead of calling this removed numbers, let's have this replaced numbers. And instead of having a set, I'm going to make this just an empty list. And you'll see why in a minute. So we're going to keep track of our smallest number, and then we're going to keep track of any numbers that we've put back into our set. Then when we pop the smallest, what can we do? Well, we either pop the smallest number that we have from this smallest, or we need to check to see if we have anything smaller in these replaced numbers. Remember, these replaced numbers are just filling in the gap between 1 and smallest. So let's check that first. Let's say if we have some number in our replaced numbers, then that number is the smallest number. All right, so if there is something in our replaced numbers, then we'll just return replaced numbers at index 0. Well, let's see, I need to pop it out of replaced numbers, so I actually have to remove it from the replaced numbers. So let's do that first. Now I'm going to say pop at index 0 because I am going to later on sort these values so that we always keep the smallest replaced number at index 0. And then we can return our result. So now if we don't have any numbers in our replaced numbers, then our smallest number is just this smallest number. So in this case, we'll say our result is equal to our smallest number. And then we need to update our smallest number with a new smallest number because we're popping this smallest number out of our set. So then we have to say self.smallest plus equals 1, and we will return our result. All right, and now in our add back. Well, at this point, we just need to add back a number that may or may not have been removed. So we only add back numbers that have been removed, which means that it has to be less than this smallest number. So first we'll just check that. If num is greater than or equal to, if it's greater than or equal to our smallest, well then we don't need to add it back because anything above our smallest is implicitly in our set because it was in the set from the very beginning and we haven't gotten to any numbers above our smallest number yet. So we can just return at this point. Nothing happens. Okay, if the number is less than our smallest set, well now we're going to have to add this back into our replaced nums, but I only want to add it if it's not already there. Because sets contain unique values, we don't want to have duplicate values. So first we'll have to check if num is not in our current replaced nums. Well, now we can add this num back. So then we'll put this number in our replaced nums. All right, so we'll append the num to our replaced nums. But then we do have to do our sort because we want to keep the smallest number at index 0 of our replaced nums at all times. All right, so I think this should do it. Let's take a quick look at this. So we have one index that represents the smallest number that we have popped, or that we haven't popped so far. And then we have the replaced numbers, which is a list of all the numbers that we have popped but we put back in. All right, then we have our popped smallest. So when we pop the smallest, we'll check to see if we have anything in our replaced numbers. If we do, then those numbers, by default, they have to be smaller than our smallest number. So those are going to be the smallest numbers so far. We'll just grab the smallest of those smallest numbers by popping at index 0, and we will return that result. Otherwise, if we don't have any replaced numbers, then our smallest number so far is going to be the number at our smallest index here. So we'll just grab that value, then we'll update our smallest to be the next smallest, and we will return the result. And finally, if we're adding something back into our set, we know that it has to be smaller than our smallest so far, otherwise we haven't popped it out. So if it's greater than our smallest, we'll just return. We don't need to do anything. If it is smaller than our smallest number, that means at some point we did pop it out and we need to put it back. So first we'll check to see, did we already put this back? So make sure that it's not already in our replaced nums. If it's not, then we will put it into the replaced nums. And then we will sort our replaced nums so that we can keep all the smallest numbers at the beginning, making it easy to pop them out when we need to. Oh man, let's see if this works. And that works. Let's see how we do. And we crush it. All right, so we beat 92% for runtime and 99.45% for memory. That is fantastic. Not only is it great in runtime, it's amazing in memory. So can we improve this? Probably, but I'm going to leave that up to you. See if you can do better. Beat my 92% and beat my 99%. All right, well, I hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code. All right, I'm just going to play a little bit since we have time. I don't know if there's much I can do here. One thing I could do, instead of doing this return, we could just say, if this is less than, it's the same thing. All right. Might be a little bit easier. That actually does worse. Okay, we could also do if it's less than and. At this point, I'm just sort of tweaking some minor things. I don't really expect this to make much difference, but it might be worth a try. Oh, and that does it. We are at 100% for runtime and 88% for memory. I don't know which I like better. Having a 90+% for runtime and a 99% for memory, I almost feel like that's better than 100% for runtime and 88% for memory. All right, well, that's it for me. Hope you enjoyed this. Hope you had fun. Hope you learned something. Please go out and write better code.